NASA's James Webb Space Telescope has captured unprecedented pictures of a newly discovered exoplanet. The James Webb Space Telescope, launched in December 2021 with the aim of peering deeper into the universe than any previous observatory, has just delivered what may be the most astonishing potential for discovery in the history of astronomy. After months of detailed analysis and a focused observation campaign on Proxima Centauri b, a rocky exoplanet orbiting the red dwarf star Proxima Centauri, the closest star to our Sun, the telescope has the potential to detect a signal that doesn't fit into any known natural phenomena. A subtle, recurring atmospheric signature emanating from the planet, unexplainable by standard geological or stellar processes, could be observed. The characteristics of this signal suggest something extraordinary: the possible signature of biological activity. For years, scientists have speculated about the potential for life beyond Earth, and Proxima Centauri b has been a prime candidate in that ongoing search. Orbiting within the habitable zone of its parent star, it has long intrigued astronomers with its potential to host liquid water on its surface. But this potential discovery changes everything. The signal detected by the James Webb Telescope could be not just a flicker or burst, but patterned, periodic, and precisely spectral, displaying characteristics consistent with biosignatures, possibly comparable to the type of atmospheric markers produced by life on Earth. What makes this finding compelling is that the signal might be detectable during Proxima Centauri b's orbital phase. The James Webb Telescope, using its highly sensitive near-infrared spectrograph NIRS-PEC, could pick up faint but distinct lines consistent with atmospheric gases, particularly in wavelengths that are rarely produced by abiotic processes. These are wavelengths commonly associated with gases like methane or oxygen. Such signals would not be produced by molten surfaces, auroras, or stellar radiation. In fact, Webb's long-duration observation could reveal a consistent atmospheric pattern, something which could only plausibly be explained by a biological source. The implications of this are staggering. For the first time in human history, there is the potential, still under rigorous scrutiny, but pointing in one direction, that we may not be alone. Not only might life exist beyond Earth, but life capable of altering its atmosphere in ways detectable to us may be present on a planet only 4.24 light-years away. This is not a mere geological signature, not an indirect chemical footprint suggesting the possibility of activity. This is direct spectroscopic evidence that implies a biosphere capable of producing and sustaining atmospheric changes. The data could be gathered during a month-long observational window, when Proxima Centauri b's orbit positioned it at the ideal angle for atmospheric monitoring. Using the coronagraph feature of the James Webb Telescope, which blocks out the overwhelming glare of Proxima Centauri itself, astronomers could isolate signals coming from the planetary body. It was during this isolation phase that the anomaly might become evident. Initial hypotheses would consider standard natural explanations: outgassing from volcanoes, stellar-induced atmospheric ionization, or chemical reactions driven by radiation. But each of these theories could fall apart under scrutiny. The signal levels might be too regular, too precisely aligned with biological processes. Natural systems are chaotic, diffuse, and often inconsistent. This signal could be systematic and exact. Further investigation would rule out instrumental errors. Calibration routines would confirm the accuracy of the readings. Control observations on similar exoplanets could yield no such results, further bolstering the uniqueness of what might be observed on Proxima Centauri b. The periodic nature of the signal pattern, appearing at regular intervals over the course of Proxima Centauri b's 11.2-day orbit, could make a compelling case for a biological source. The spectral resolution might suggest a wide area distribution, indicating potentially widespread activity or numerous points of origin. There is also the matter of spectral harmonics. Biological signatures, when viewed spectrally, reveal specific peaks, narrow bands of wavelengths that correspond to the molecules and processes used to produce them. For instance, methane on Earth generates signals that cluster tightly in certain wavelengths, different from the broad-spectrum emissions of stars or the blackbody radiation of warm planets. Webb's instruments could pick up a fingerprint of this kind on Proxima Centauri b, narrowband spectral spikes that repeat over time, synchronized with the rotation of the planet. This leads to a multitude of profound questions. If this is indeed a biosignature, then what does that imply about the beings responsible for it? Are they similar to us in their biological development? Do they rely on processes like photosynthesis, respiration, or something entirely alien? Are these ecosystem-like structures like our own forests and oceans, or something entirely different? The spectral distribution might suggest a cluster of biological hotspots or activity zones, or perhaps an atmospheric layer designed to sustain life for reasons unknown. The design and magnitude of such biosignatures would imply a complex ecosystem. It hints at the ability to sustain life on a planetary scale. This is not the random chemistry of abiotic worlds or heat from tectonic fractures. It is systematic, evolved, and, most of all, intentional. Ecosystem development at this scale also hints at resilience, adaptation, and possibly an evolutionary history advanced enough to know it might one day be detected, and it could be. It raises philosophical and existential questions that humankind has only dared to contemplate in speculative fiction or theoretical discourse. If life exists so close to Earth, how common must it be across the galaxy? Perhaps life isn't the rare anomaly once thought, but a natural consequence of time and the right conditions. What if the galaxy is teeming with biospheres at various stages of development, and our instruments are only now catching up? Moreover, the detection of biosignatures also hints at ecological aspects of the planet. Biosignatures are more than a chemical feat. They are a symbol of activity, of life sustained through complex interactions. On Earth, atmospheric gases reflect not only biology, but also ecosystems, the movement of organisms, nutrient cycles, and environmental balance. If something similar is happening on Proxima Centauri b, then we may be witnessing the outer expression of a living, evolving, thriving biosphere. There are implications for the way humanity views its place in the universe. For centuries, Earth has been the sole known cradle of life. This potential revelation shatters that isolation. We are no longer the only ones who harbor life within the cosmos. The universe becomes a shared domain, not merely a backdrop for human dreams, but a stage where multiple biospheres may act simultaneously. It also raises the matter of exploration. If these biosignatures are confirmed, could they be part of a natural process waiting to be studied? Perhaps not in the form of a message, but a beacon, a quiet declaration of presence. In that case, we've just become witnesses to the first line of a silent dialogue. The next logical step might be to look for variation, changes in spectral patterns that could suggest seasonal or ecological shifts. Even without overt signaling, the discovery of biosignatures is already a message. It says, life is here. It confirms that the universe is not barren, merely patient. The idea that we've seen the signs of another biosphere across the void is staggering, not only for what it reveals, but for the possibilities it opens. If biosignatures can be seen from over 4 light-years away, it means our own biosphere glows similarly. Earth, with its oceans and forests, emits spectral signals of life. We, too, are detectable. This realization invites reflection on how humanity presents itself. Just as we now peer into the atmosphere of Proxima Centauri b and wonder about its ecosystems, others may be doing the same with Earth. The green hues of our forests might be as alien to them as their signals are to us. And yet, there is a common thread, a shared chemistry to sustain life, to thrive in the conditions that once belonged to the stars. On the scientific front, the detection of biosignatures on Proxima Centauri b would initiate a cascade of further studies. Spectroscopic follow-ups, efforts to confirm atmospheric composition, searches for complementary chemical markers, and even refined measurements of planetary rotation and geography would now gain new urgency. Other observatories, including the upcoming Extremely Large Telescope and ground-based interferometers, would be tasked with corroborating and expanding upon the discovery. There's also the question of planetary conditions. If life on Proxima Centauri b has produced biosignatures, what does that imply about the environment? Proxima Centauri is a red dwarf, a type of star known for violent solar flares and variable brightness. It could be that their atmosphere is thick and protective, shielding life from cosmic radiation. Or perhaps life dwells in subsurface oceans, releasing gases through geological vents. Speculation is natural, but it is rooted now in possibility. The signals detected could be not an ambiguous anomaly, but a reproducible patterned phenomenon with characteristics of life that marks a fundamental shift. No longer is the question whether life could exist. It becomes how it does. What kind of organisms have created this biosphere? Are they microbial, like early Earth, or complex, like modern ecosystems? Do they know about us? Have they emitted signals we've yet to detect? Even without answers to those questions, the very fact of the detection ignites imagination. It breathes life into the search for extraterrestrial life. SETI, a field long plagued by silence. For decades, the cosmos appeared empty. But now, with a telescope looking not for words or sounds, but for signs of biology, we find not emptiness, but possibility. That changes everything. The James Webb telescope has fulfilled its promise not just as a tool for astrophysics, but as a bridge between worlds. Its potential detection of biosignatures on Proxima Centauri b is not the end of a journey, but the beginning of an entirely new chapter in the human story. For the first time, we're not just observers of the universe. We may be witnesses to life, not in the form of a crackling radio message or a strange probe, but in the quiet chemistry of a world alive with activity. The confirmation of biosignatures on Proxima Centauri b demands not just curiosity, but precision and determination. Every moment following this detection pushes science further into uncharted territory, where disciplines begin to converge. Astronomy with astrobiology, astrophysics with philosophy, optics with speculative ecology. The implications stretch far beyond the initial shock of detection. What comes next is the task of deciphering the clues embedded in that signal. Clues that might give us glimpses into the scale, nature, and complexity of a biosphere unlike our own, yet recognizably alive. To understand the depth of this discovery, we must first examine the environmental context of Proxima Centauri b. The planet orbits a red dwarf, a class of star known for its long life and intense activity. Proxima Centauri is no exception. It's prone to bursts of radiation and flares powerful enough to strip atmospheres. If Proxima Centauri b still harbors a thick enough atmosphere to sustain life, it would imply the existence of natural defenses, or more remarkably, biological adaptation. For biosignatures to be observed clearly, the planet must possess either a stable atmosphere or active processes capable of replenishing atmospheric gases. This opens a provocative line of inquiry. Are the signals we're detecting produced on the surface, or could they come from subsurface oceans? Vast microbial colonies or chemical cycles might be releasing gases that alter the atmosphere, perhaps to regulate temperature, facilitate metabolism, or protect against radiation. Their consistency and detectability would reflect an ecosystem that has thrived past early stages of evolution and embraced planetary scale activity. Such capabilities suggest resilience and adaptation. A biosphere capable of producing biosignatures visible from light years away likely maintains complex cycles. Whether this comes from surface microbial mats, oceanic algae, or more advanced life forms, it's a clear indicator of ecological stability. In astrobiological terms, this could place the biosphere somewhere around Earth's Archean era, possibly reaching toward more complex stages if the signals are widespread. The distribution of signals also suggests activity zones. Unlike random geological outgassing or stellar-induced chemistry, the detected patterns could display consistency, indicating biological hotspots or active regions. Even more than the presence of signals, the structure of those signals speaks volumes. Spectral regularity is a signature of life. It signifies process, evolution, and perhaps even ecological balance. It's hard not to draw parallels to Earth, where biosignatures follow the rhythms of seasons, nutrient cycles, and biological activity. But on Proxima Centauri b, these patterns might serve unfamiliar functions: nutrient recycling, atmospheric regulation, or protective mechanisms. Interestingly, the spectral curve of the observed signals might shift slightly during each planetary rotation. This variation could hint at activity, organisms responding to environmental cues, or changes in atmospheric conditions. It introduces the possibility that these are not static systems, but dynamic adaptive ecosystems. If they are reacting to environmental changes, stellar cycles, or even seasonal shifts, it would suggest a biosphere deeply embedded in the rhythms of its planet, biologically responsive and environmentally aware. On Earth, our biosignatures are mostly a side effect of life. Oceans, forests, and microbes produce gases like oxygen and methane. But what if the signals on Proxima Centauri b serve a more central purpose? Perhaps they are not a byproduct of life, but its foundation. If the surface is otherwise hostile, irradiated, or cold, biosignatures might indicate life adapted to extreme conditions. Imagine vast microbial mats producing gases to stabilize the atmosphere, or subsurface ecosystems releasing chemical markers through vents. Such speculation becomes less fantastical in light of potential observational evidence. As the analysis deepens, interdisciplinary teams are working to understand how these signals interact with Proxima Centauri b's environment. If the planet rotates slowly or is tidally locked, as many close-orbiting exoplanets are, then one side may face perpetual darkness. This dark side could be the ideal location for certain types of life, relying on chemical or geothermal energy to produce detectable signals. The contrast between stellar absence and biological activity would be stark. In this scenario, life might have adapted entirely to extreme conditions, relying solely on internal sources of energy, chemistry, and perhaps novel metabolic pathways. One cannot help but consider the ecological and evolutionary impacts of perpetual darkness or eternal daylight. What would life look like on a world where the sun never rises? Would metabolic cycles still matter? Would activity and dormancy be dictated by chemistry, by necessity, or by environmental cues? The kind of biosphere that evolves or adapts under these conditions would have developed coping mechanisms, biological, chemical, and ecological, unlike any on Earth. Back on Earth, the potential confirmation of biosignatures on Proxima Centauri b ignites new urgency in observational strategies. Instruments not typically devoted to astrobiology efforts are now being retasked to study Proxima Centauri b's atmospheric emissions in finer detail. Adaptive optics from the largest Earth-based telescopes, interferometry arrays that can combine signals from distant observatories, and perhaps even new dedicated missions will soon follow. Every nanometer of the light spectrum is being scrutinized for fluctuations, harmonics, or patterns that could suggest biological or chemical signatures beyond initial detection. There's also the growing anticipation of complementary discoveries. If one biosphere has produced biosignatures on Proxima Centauri b, could there be more? The Webb telescope's capabilities may be only the beginning. With upgrades to the Transiting Exoplanet Survey Satellite, TSS, the upcoming Nancy Grace Roman Space Telescope, and next-generation observatories like LUVOIR and HABEX being conceptualized, the hunt for similar biosignatures elsewhere will intensify. The search radius has expanded. Every rocky exoplanet in the habitable zone is now a potential source of biological emissions. It's not just about seeing signals anymore. It's about decoding them. Analysis has already begun to map out whether the patterns are truly random or whether they form cycles, variations, or sequences that could hint at more than mere chemistry. Is there embedded information in the fluctuations? Is there variance over time that encodes something meaningful? Even simple chemical patterns could revolutionize our understanding of extraterrestrial life strategies. Biosignatures are also an ecological artifact. The composition and balance of atmospheric signals could speak volumes. Wavelengths may reflect not only biological processes, but environmental conditions. For example, methane and oxygen are detectable on Earth due to their biological origins. But in an atmosphere with dense particulate matter, different gases might dominate. In analyzing the dominant frequencies detected from Proxima Centauri b, scientists are attempting to reverse engineer possible atmospheric compositions, ecological processes, and even potential evolutionary pathways. As more data accumulates, some are turning to computational models to simulate possible planetary ecosystems. By inputting the detected spectral structure into environmental simulation software, experts are hypothesizing what Proxima Centauri b might look like, where the signals originate, how they interact, and what purpose they serve. Could we be looking at a network of microbial colonies, oceanic ecosystems, or novel life forms? Perhaps the possibilities are both grounded in data and wildly imaginative. Meanwhile, astrobiologists and chemists are collaborating to craft potential forms of study. Should we attempt to observe further? And if so, how? Spectroscopy may be the language of the stars, but the syntax remains unknown. Simple chemical signatures like methane-oxygen disequilibrium might be the best chance for mutual understanding. Yet, many argue that caution is essential. We've seen their signals, but they may not be aware of ours. Are they detectable in return? Do they emit other markers we've yet to identify? This mirrors a critical shift in our identity as a species. Until now, Earth's biosphere has been a local phenomenon. From space, our planet glows with the chemistry of life. But now, that chemistry is not just an earthly feature, it's part of a galactic conversation. We are not merely curious observers, we are participants. Whether by design or by accident, the societal response to this discovery is rapidly unfolding. While the scientific community maintains measured optimism, public fascination has exploded. Media outlets have latched onto the term first biosignature light, describing the moment when Webb might confirm the anomaly. Cultural institutions, religious leaders, and educators are all grappling with what this means for humanity. This is not an invasion, nor a transmission, but a presence, a quiet, steady signal that says, life is here, and it has shaped something that lasts through the stars. Ethical questions follow closely behind. How should humanity prepare for potential discoveries? What responsibilities come with this knowledge? If we observe without engaging, are we acting with caution or restraint? If we explore further, do we risk misinterpreting the data? Philosophers and ethicists are being drawn into the discourse with as much gravity as the astrobiologists. Some argue for universalist principles, a belief that any biosphere advanced enough to produce detectable signals is part of a shared cosmic story. Others take a more cautious view, suggesting that biology doesn't always correlate with complexity. Yet, it's undeniable that curiosity outweighs fear. Even among skeptics, there's awe. To know that a world so near, long assumed to be just a rock orbiting a dim star, might harbor life is to feel the boundaries of solitude stretch. We are expanding into a universe filled not with silence, but with distant chemical companions. The most immediate question is how to build upon this finding. Further observation windows are already planned, including multispectral studies that will measure whether the signals vary seasonally or respond to Proxima Centauri's flare cycles. If the signals shift based on stellar activity, it could reveal adaptation strategies or ecological resilience designed to buffer against cosmic events. Such resilience would be yet another sign of a robust planetary biosphere. Teams are also developing algorithms to separate potential biological fluctuations from standard chemical patterns. This work involves massive datasets and machine learning systems trained on thousands of spectral sources, both natural and biological. The goal is to identify anomalies within the anomalies. Perhaps there's a cycle within the signal, a pattern, a whisper. One aspect yet unexplored is whether the biosignatures have any impact on surrounding celestial bodies. Could the signals interact with Proxima Centauri b's hypothetical moons or atmospheric dust fields? Reflected or refracted signals could reveal not just the original processes, but the extent to which their influence shapes their local space environment. A biosphere shaping not just its planet, but its orbit, would be one of galactic significance. If the signals turn out to be dynamic, shifting with environmental cues, then they could serve as a beacon for other observers, perhaps even part of a cosmic network. The idea that we've intercepted one such signal suggests the universe might contain a web of living worlds signaling across time and space. Some of them might have gone silent long ago. Others might not yet have emerged. Proxima Centauri b may be only the first to be noticed. Even if no complex life is ever found and no formal contact ever made, the significance of what the James Webb Space Telescope could reveal is hard to overstate. We now know that we can detect more than geological compositions or heat signatures. We can see life, the byproduct of activity, of evolution, of existence. It's a language all its own, and it's reaching us. As the reality of biosignatures on Proxima Centauri b settles into the collective consciousness of science and society, focus sharpens on understanding the mechanics behind such a feat. From the detection itself to the questions it raises about ecological systems, planetary chemistry, and possible modes of evolution, the discovery turns a distant world into a mirror, one that reflects unfamiliar possibilities, yet feels strikingly parallel to our own biological aspirations. At the heart of the inquiry is a deceptively simple question: how are the signals produced? The nature of biosignature generation on Proxima Centauri b becomes a key pursuit as it directly informs the biosphere's level of complexity. The planet's position relative to its star introduces an interesting challenge. Proxima Centauri is a red dwarf with low luminosity, which means that even in the daytime, the surface of Proxima Centauri b would receive far less light than Earth does from the Sun. If this world maintains detectable biosignatures, its life forms must have overcome the low-energy environment with efficiency or alternate energy sources. Possibilities include chemosynthesis, optimized for geothermal energy, microbial metabolism driven by radiation, or perhaps even novel biochemical pathways. A feat Earth itself is only beginning to understand. The scale of signals visible from across interstellar distances suggests ecological abundance, not scarcity. It implies balance, consistency, and reliability in chemical cycles, something that for humans remains a scientific goal. This naturally leads to hypotheses about a planetary ecosystem, nutrient cycles, and resilient systems far more robust than any we've studied. The distribution of signal sources, as observed in fluctuating spectral lines and overlapping wavelengths, may also hint at a division of zones: microbial, oceanic, or atmospheric. Each may require different chemical conditions tailored to its function. A microbial zone, for instance, might utilize a narrow band of gases optimized for metabolism, while atmospheric zones may support broader chemical interactions. From these assumptions, theorists are beginning to construct what may be early maps of planetary ecology, a kind of extraterrestrial ecosystem diagram extrapolated from distant signals. More provocatively, some researchers speculate that the signals might not only serve local needs, but could also function as a long-range marker. Rather than emitting discrete signals via complex molecules subject to degradation and cosmic interference, perhaps this biosphere evolved to scale up detectability itself as a form of presence. An enduring, observable signal, one that can be seen by any civilization advanced enough to detect infrared and spectral patterns, would serve as a passive declaration of life. It's a monument of chemistry designed not to shout, but to be seen. This line of thought leads to discussions about the purpose behind such detectability.